This will be the second part of the dynamical system and Markov chains video. So from the previous video, we know that the market share of channel 1 and channel 2 can be expressed in the form of a matrix, and the channel 1 has 45% of the market and channel 2 has 55 after 1 year period. So this square matrix where the sum of the columns is a probability vector is called a stochastic matrix. This should be the probability factor, and when you put them into a matrix form, this will be known as the stochastic matrix. So you have the second year prediction for the first channel and channel 2, and then eventually you can calculate for the third, the fourth, fifth, and so on, where the calculation can be simplified into this equation. So the n plus 1 year will depends on the probability matrix multiplied with the preceding year, which can be summarized from here. So this S2, which means that the n plus 1, and this 0.45 and 0.55 is actually the original, the previous year, the first year. And the 0.8, 0.9, and 0.1, 0.2 here can be put into a stochastic matrix form. So this is in column. 0.8 is for the remain, 0.2 is captured by market share 2. Okay, remember in the class that I told you, you just need to make a tape matrix here. So let's say this is the channel 1, this is channel 2, and the first row is channel 1, channel 2. So this entry will be corresponding to channel 1 remain in channel 1, and this entry will be channel 1 move to channel 2, and this entry will be channel 2 move to channel 1, and then we have another one, the last one is channel 2 remain in channel 2. So this is how you construct the stochastic matrix. Then if we are going to read it, the P11 will be the first one, 0.8. Probability that a channel 1 viewer remains a channel 1 viewer, and so on for the rest of the figure. So a Markov chain is a dynamical system whose state vectors at the succession of time intervals are probability vectors, and for which the state vectors at successive time intervals are related to by equations of the form: the following years, this is the outcome, equivalent to the stochastic matrix multiplied with the vector of the previous years. So P is known as the stochastic matrix or the transition matrix for the system. Now let's look at another example. Here is the wildlife migration as a Markov chain. So if you read the example from the textbook, or maybe the questions from the textbook, this is the diagram that I summarize it out. So you need to know how to interpret or how to draw this, sketch this diagram. It will ease your understanding and answering the calculation later on. So if I'm looking at the reserve 1 here, so 0.5 here means that the lion will remain at reserve 1 after 1 month, and the 0.3 here means that the lion will move to reserve 3 after 1 month, and 0.6 here means that there's a probability, 60% of probability that a lion in reserve 3 will move to reserve 1. And for the following movement of the lions, you could try to interpret it yourself. So assuming that T is in months and the lion is released in R2 at time T0, so track its probable locations over a 6-month period. Now the first step for you to solve these equations will be try to define the state vectors. You must define a state vectors before you start it. So let's imagine that x1, x2, x3 be the probability that the lion is in reserve 1, reserve 2, reserve 3 respectively at time t. So you have a xt vector, which is the state vector at that time, the probability of the lion at a particular reserve. Now that you have the state vectors, the second step is define the initial state vector. So initial means that the time will be 0, and So you will have a x0, x20, and x30. So this information you have to extract from the question here. And because the lion is released in region 2, so you only have one possible outcomes. The lion is at reserve 2. That's why you have a 1 here corresponding to the probability of the lion at reserve 2. The rest are 0 because there's no way for you to split the lion into half to be at 2 locations at the same time. So once you have the state vectors and the initial state vector, the third step is to construct the transition matrix. So remember I told you in the class, or maybe I showed you here, how to construct the stochastic matrix, this one. So what you need to do is, the first row will be the row here will corresponding to the region 1, 2, 3, and the column here 1, 2, 3. So if I'm going to read it, from reserve 1 to reserve 1 is 0.5, which means that the lion will remain at reserve 1 after 1 month. Or maybe the lion will move to reserve 2, we have a 20%, and reserve 3, 30%. And for this one, 0.4 is reserve 2 move to reserve 1, and so on. You need to know how to construct this transition matrix. And the last step will be to solve it using this equation. Okay, the location at a particular time is equivalent to the transition matrix multiplied with the location or the probability in the previous month. So you have the x1 equivalent to p, the transition matrix, multiplied with the original one. And the second year will be based on the first year, the third will be based on the second year, the fourth will be based on the third year, the fifth will be based on the fourth, and so on. And apparently, based on those steps that you have calculated, you can see that x1 is p x0. So which means the 1 here is the time, the 0 here is the time when initial time. So the second year equivalent to first year, third, and second. So eventually I can write it in this way. The second year is p, remember p, and the x1 is actually from here. So you have the p x0 here, and multiplying the p together will be p squared x0. If you have the third x3, the third month, sorry, it should be month, the third month, so you have a p multiplied with x2. So x2 you found out here is p2 x0, so you substitute the p2 x0 here, and then you have the p3 x0. So Markov chains in terms of power of the transition matrix is when you have these equations, the xt is equivalent to the p raised to the power of a certain number multiplied with the x0. So using this, you can find the state vectors directly from the initial state. So you just need to know what is the transition matrix and what is the initial conditions. You can find the location of the lion after maybe 3 months, 5 months, 10 months, 11 months, or 24 months. You just need to raise the power of the matrix T to the particular months that you want and multiply with its initial condition. So knowing this method actually save your time. You don't need to calculate all the second year, the third year, the fourth, the fifth, the sixth, and so on in between the months that you want to calculate with the initial one. So this is one of the applications of the Markov chain.